Okay, we now get to the next lab. Make sure that I share screen this time. Okay. Okay, so this one is going to be on extrasolar planets. I really love this topic. The planets that we have discovered outside of our solar system that are going around other stars, extrasolar planets. Okay, so introduction. Welcome to Lab 8, Extrasolar Planets. Even without technology to directly view planets beyond our solar system, recent developments in indirect detection methods have led to the discovery of more than 500 planets. It's actually right now the count is close to 3,000, I believe, and rising, uh, orbiting stars than the sun. These planets are known as extrasolar planets. In this lab, we will examine how indirect methods, such as Doppler shift techniques, are used to discover and study extrasolar planets. At the end of the lab, you will build your own solar system. So this chart shows you the 1AU. So if you look at our solar system, we've got the sun. Earth, by definition, is 1 AU away from the sun. That's astronomical units. So, and then it tells you the distance of the other planets. Mars is about 1.5 AU, you see, from the sun. And those are the inner planets. And then you got Venus and then Earth. So now it shows you some of the other extrasolar planets we have discovered, like this one, Tau Bootis, and look at how close this star is to the planet is to its star. And not only that, it's actually the mass of Jupiter, 3 times 8 times mass of Jupiter. It's heavier than Jupiter. So this is something that's not found in our solar system. These extra hot, big planets called hot Jupiters. They're called hot Jupiters, and they are so close to their host star. That's kind of what makes them easier to discover. Because they're so heavy, those were the first set of stars we discovered, those heavy ones. So you see, in our planet, in our solar system, Jupiter is way over here. Jupiter is about 5 AUs from the sun, so it would be that far away, right around here. Whereas these planets are close. 51 Pegasi was the first extrasolar planet that was discovered ever, 1995. And look how close that one is, 0.47 mass of Jupiter. And then some of the other one, they're so close. Look at them. But now these ones are a little bit farther away. 16 Cygnus B, and then now we're talking a little bit farther. 47 Ursae Majoris, and then Gliese 614. So this one, almost the distance of kind of where our asteroid belts would be. Our asteroid belts are right around here, between 2 and 3 AUs. That's where our asteroid belt is. But that planet happens to be 2.5 AUs from its host star. So that's kind of a nice chart there. So the learning objectives describe how the mass and orbital characteristics of an extrasolar planet can be measured using Doppler shifts and by using Kepler's third law. Describe how the size and density of an extrasolar planet can be measured using planetary transit information. And then explain what the hot Jupiter problem is and why it occurs. That's the hot Jupiters, or these ones right here. They're so big, they're like heavy, like Jupiter, and plus they're hot because they're so close to their host star. So now to go back, you just exit out of it like that, and then now you could go to the next one, Doppler Wobble. So to date, over 3,000 planets have been discovered orbiting stars other than the sun. in our solar system, is our solar system unique, or are there other solar systems with planets in orbit around their stars? Well, we're not unique. Definitely, that's what we've been discovering. Until recently, the search for such extrasolar planets had been unsuccessful because detection methods were not sensitive enough. But now instruments and techniques have improved and continue to improve, and the search is beginning to yield a wealth of results. Extrasolar planets are most easily found by observing a wobble in the motion of the parent star caused by the gravity of the unseen planet. This wobble means that the star itself is not stationary, but instead both it and the planet are orbiting the center of mass for the two bodies. So you see here, this is, let's see here, let's minimize it a bit. Yeah, so the animation shows the star and the planet orbiting their center of mass. The center of mass is a white dot. Okay, so you see this is the star, and this is its planet, companion planet. And imagine this is light years away, you know, and the only thing that you can see through your telescope is maybe the star. You can't see a planet because the star's brightness completely overwhelms the brightness of the planet. So you only see this guy, but you see this thing wobbling like this star wobbling. And as it's wobbling, it's coming toward you and away from you. And therefore its spectral lines are Doppler shifted towards you, away from you, towards you, away from you. So if you did the Doppler shift extra credit, the lab, you will have learned that when stars come toward you, their spectral lines are blue shifted, and when stars go away from you, their spectral lines are red shifted. So then that's kind of what you will experience. You see? So imagine, for example, the Earth is on this side, on the left side, and then you see this green star coming toward you, away from you, toward you, away from you. And then its spectral lines are constantly being blue shifted, red shifted. You see? So in other words, if you are, oh, I see. I wish they did it where we could stop it in a second. Okay, I got the idea there. So this is the Doppler wobble, we call it, the wobble of the star. As a planet orbits a star, it pulls on the star and causes it to move as well. Both objects end up orbiting their center of mass. You see? So if you have a hot Jupiter, of course, if it's very big and heavy, it's going to cause the center of mass to be outside of the planet's body center, and the wobble of the star is going to be considerable. For our Earth, for example, we're not that heavy. So the center of mass of the Earth-Sun system is actually inside of the sun, somewhere here. And so the wobble of our sun due to the motion of the Earth, due to the gravity of the Earth, is very, very small and very hard to detect several light years away. But if this planet is big, then it has a detectable influence on its star. So it says here, R is the total separation between the star and the planet. And then D1 is the distance from M1 to the center of mass. And D2 is the distance from M2 to the center of mass. Which one, when one mass is much larger than the other, the center of mass of the two bodies is located so close to the larger mass that when viewed from a great distance, the larger mass may hardly seem to be moving. All right, that's what I was saying earlier. This is the typical case with the planet and its parent star. So they gave you here an equation. The mass of this star times that distance is equal to mass of that star times that distance. And that the sum of the two distances must be equal to the distance between the stars. R is the separation distance from their center of mass. The sun is 1.1 1047 times more massive than Jupiter, called the mass of the sun M1 and that of Jupiter M2. The ratio M1 to M2 is 1047. If the first equation is divided by M2, we find that D2 is 1047 D1. So in other words, if this was Jupiter and this was the sun, this D2 from here to here would be equal to 1047 D1. So because the sun is 1047 times heavier than Jupiter, the distance from their center of mass to the center of Jupiter would be 1040 times bigger than the distance from here to here. You see, that's what they're saying there. The sun moves around the center of mass in the Sun-Jupiter system in an orbit about 1,000 times smaller than Jupiter's orbit. This motion for the sun is small, but not insignificant, you see. So if we were in another solar system trying to look back at our solar system, the influence of Jupiter's gravity on the sun would probably be still detectable if we were an advanced civilization. You see, see, as this gets heavier, the center of mass gets closer to that one. This animation shows a change of location of center of mass for two bodies according to the changes of the mass of one of the bodies. So if I make this guy heavier, then the center of mass gets closer to that. And if I make it even heavier, the center of mass can actually go inside of it, like right around there. Center of mass exercise. So using the equation and the Sun-Jupiter example above, what is R in terms of D1, given the value of D2 listed above? Okay, so basically they're saying you already know that D2 is equal to 1047 D1, right? And then you know that the R is the sum of the two, D1 plus D2. So this should be pretty straightforward. So again, show the calculation for this, how you did it, and then put in the answer, and then submit, and then put what score you got. Then go to question 2. If R, the total distance between the sun and Jupiter, is this, what is D1? Okay, so again, you could show the calculation for that. So they're giving you the R, and then based on the relationship that you found in question 1, you can solve for the D1, right? And then D1 is going to be this guy. From here, they're giving, if you know the distance from here to the Jupiter, you should be able to find the distance from here to the center of mass. That's the D1 that they want. Show the calculation for that, and then again, your result, take a picture of your result. Question 3. The sun has a radius of this. Is the center of mass for the Sun-Jupiter system inside or outside the sun? Okay, that one you don't have to show calculation, but just an answer. And then based on your answer that you got in the previous question, you should be able to answer this, and then take a picture of that. And I think that's it for that. So it's kind of just getting you used to doing center of mass calculations. So now measuring radial velocity. It is currently impossible to directly see the motion of a star other than our sun, due to the influence of a planetary companion. Instead, astronomers detect small changes in a star's motion using the Doppler effect. So you see, it's showing when the star is coming toward us as it's wobbling, when it's coming toward us, its spectral lines are blue shifted. That means they're shorter, you see? And when it's moving away from us, they are red shifted, they're longer. Although in principle, one could detect the wobble of a star through direct observation, in reality, this is incredibly difficult. It is akin to standing in New York City and measuring the width of a coin held up somewhere in Kansas. Oh my gosh, that's crazy. So imagine the precision you would need. It is easier to detect the wobble by measuring the radial velocity of a star, which is measured by observing the Doppler shifts. The orbit of a star makes its light blue shifted, shorter wavelength when it's moving toward, or red shifted. No, I thought that was like an animation. Okay, so this method is called the radial velocity method or the Doppler Wobble method. So two names for it. It can best detect planets at least the mass of Jupiter with an orbit near a star. The only thing bad with this technique is if the planet is not that heavy and if it's far from it, the star, it's not going to work that well. It's not going to make its star wobble that much. So inclination angle of planetary orbit. We do not always know the plane that an extrasolar planet is orbiting on. Therefore, we can often only predict the minimum possible mass or range of masses for a planet. Because the planet might be orbiting in, let's say, here's the star, its host star. The planet doesn't necessarily orbit in a plane that's parallel to its line of sight to us. You see, so this is the Earth right here where the observer is, right here, you see, that's the Earth. So the plane of orbit of that planet might be inclined at a certain angle, you see. It might be coming down, and then going back up, coming down, going back up, like that, you see. So that's called an inclined orbit. So one important consideration concerning planetary orbits is that the plane of orbital revolution for a planet is not usually perpendicular to our line of sight. For most extrasolar planets, there's no way to determine the tilt angle with complete reliability. This can create uncertainty in the orientation angle, that often only the minimum mass of the planet can be determined. Right? So that means the masses that we have are more like their minimum mass. And if the planet orbit is wobbly, it's an inclined, then that means they're probably even heavier than what we think. So nevertheless, with careful analysis, it is often possible to place limiting ranges on the masses of extrasolar planets, as we shall see later. In some cases, the tilt angle can be determined rather well. In these cases, the actual mass of the planet or a range of possible masses can be determined with confidence. Still, because of this uncertainty, the mass of extrasolar planets are usually reported as the product of MP sine of I, from which the true mass MP follows when P is specified. So in other words, the mass of the planet times sine of that angle. You see, if that angle I is 90, you see where the sine of I came from? If that angle is 90, that means the orbit is actually not tilted at all. And the angle would be 90. That means the orbit would be like straight up like this, going this way, like this. You see, the planet would not be tilted. And so sine of 90 would give you what? 1, right? So that means that would give you the max, the minimum possible mass. Okay, so now we have here Doppler measurement. By looking at the Doppler Wobble plot, one can extract the pertinent information solving for a planet's mass. The following is a typical Doppler Wobble plot, which consists of the radial velocity of a star plotted versus time. From this plot, one can estimate the period and eccentricity of the planet's orbit and the maximum radial velocity of the star. The star's radial velocity changes as the planet pulls it around in a tight orbit about the center of mass. The period P is the time it takes for the star to make one complete orbit around the center of mass. So you see here, you can say the radial velocity is -50 or not necessarily negative 50. It starts around negative 48, 40, 47. Then it goes all the way to, as it's going up, 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 it goes all the way to 50, something a little bit past 50, maybe like 60 meters per second. Then it comes back down to negative. Then it goes back up to positive. So we measure the time it takes for the two maximum peaks of that radial velocity, right? And then that's going to give you the period. Okay, looks like the period for that planet is what? 1991 all the way until 1996. Wow, so the planet took 5 years. Actually, the star, I should say. The star took 5 years to wobble once, which also means that the planet took 5 years, right? So the planet and the star went around each other every 5 years. So the period for the planet and the star are the same, even though the planet has a much larger orbit. Therefore, you can determine the orbital period for the planet by finding the time between consecutive wave crests on the graph. On the graph, this is denoted by P. The quantity K is the semi-amplitude of the star's radial velocity, half of the vertical distance between the hills and the valleys. Oh, you see, so the full amplitude is from the maximum hill to the minimum valley. That's full amplitude is 2K, right? And then the K would be half of that. So it would be measured from the 0 all the way to the, let's say it's 60 meters per second. So the negative part of the curve, the valley, corresponds to the star moving towards the Earth. So when the radial velocity of a star is negative, it means it's coming toward us. When the radial velocity of the star is positive, it means it's moving away from us, you see? So the star is moving away from us very fast, then moving towards us, towards us, towards us, towards us. And then, as it's coming down, it's moving away from us slower. Then when it's 0, it's not moving away from us. Then it's moving towards us as it's going down, you see, like that. Moving, this is moving towards us. And then when it's positive, it's moving away from us. So on this plot, the star spends an equal amount of time moving towards and away from the Earth. But that is not always true. Generally, you must find the average of the maximum velocity towards the Earth and the maximum velocity away from the Earth in order to find the K. Okay, the relationship between the mass of an unseen planet in kilograms, the semi-amplitude K in meters per second, and the period P in seconds is this. So in other words, they're giving this to you in such a way that the K, you have to put the K in units of what? Meters per second, and the period in units of seconds. And then the rest, the calculator will do everything for you, and it'll give you the mass of the planet in kilograms. This equation can be solved to give MP sine I. Remember, the mass of the planet is usually expressed in terms of MP sine I because I, the orbital inclination, is often not known. Only if I can be determined will we be able to obtain the planetary mass MP directly. Exactly, you see. The mass of the star M, big M, can be found, okay, hold on. Oh yeah, this big M then is the mass of the star, the big M. Whereas the little m on the left side of the equal sign is the mass of the planet. You see, on the left side of the equal sign, MP is the mass of the planet. The capital M is the mass of the star. So how are we going to calculate the mass of the star then? It says the mass of the star, big M, can be found in a variety of ways, but that is beyond the scope of this lab. For the exercises that follow, M, P, and K can be read from the Doppler Wobble plots. Okay, so now it says here, let's zoom in a bit. So it says, we are going to find the mass of the planet multiplied by sine I orbiting the star using the equation below. First we need to find the semi-amplitude K and the period P from the Doppler Wobble. The mass of the star M will be given later. So let's plot. Okay, so this is the maximum. Okay, maximum velocity. So you see how they found the K? You go where the 0 is, you go to the right, and then you go all the way up to the peak. Then you go to the left and try to read that number as best as possible. Maybe zoom in more. You see there? It's 50, 60, 70, 80, 90, 95. Maybe you could even read it as 97, right? 60, 70, 80, 90, maybe 97. Okay, so then that will be the K value. That's calling that the semi amplitude. To find K, we must first find the total amplitude. It's the semi amplitude of the radial velocity from the 0 all the way to. That means the star's wobble has it coming towards us with the greatest speed of 95 as it's circulating around its center of mass, or between the center of mass between the star and the planet. Okay, then we minimize. Then we press play. Oh, look at that. So the bottom K wasn't the same. 65 meters per second maximum velocity towards us. So that means the maximum velocity of the star coming towards us is, it could be read, it looks like, yeah, that one looks more like a 65, like right between the 60 and the 70, maybe a negative 66, you know, negative 66. But yeah, so then you can say the 60. So that means it's not symmetrical. When the planet is coming towards us, it's faster than with the planet going away from us. So then what are we going to do now? I believe they're going to take the average of these two then. 95 plus 65. So they're taking the absolute value of the negative 65, right? So if you thought it was negative 66, you could take the absolute value of the negative 66. So then you take the absolute value of that, then you take the average of those two values and you get 160. So I mean, sorry. I mean, they're summing them up, then dividing by 2 to get their average. So their K value is 80. You see? Then you're going to do, oh, okay. Then you read the distance between peak to peak. So how do you get that? Well, you see how the first one is 45, 41, 42, 43, 44, 45. Yeah, it's maybe a slightly more than 45. Yeah, I think it's a great reading, 45.1. And then the other one is 130. Yeah, 132. It's right between 132 and 134. Hold on, let's see, 135, 134, 133, 132. Hold on, it's a wrong reading. 131, 132, 133, 134. Oh, I believe that's a wrong reading. It should be, it's between 131 and 132. So it's actually 131.5. So they read each of those small lines as a 2. You see that? So it's actually more 131.5, not 132.5. Then you're going to take the difference of those 2 times, and you're going to, let's see here. So, Okay, so then what did they do? Okay, so they just basically outright give you the mass of the star, because in this lab, they're not teaching us how to calculate the mass of the star. That's probably going to come at a later lab, right? So finding the mass of the planet, given that the mass of the star is 2.088 times 10 to the 30th, right? Then you raise that to the power 2/3. Then you go 80 for the K. Then you say, oh, how did they get the 3.146 times 10 to the 5 seconds? How do they get that? Well, they take they took how many hours was that? 132.5, they read it. Then they're going to convert that to seconds. Let's go back to the previous. Oh, okay. So 132.5 minus 45.1. Let's share the whiteboard. 132.5. I think it should have been 131.5, but let's just go with their number. Then minus, what was the first number? 45.1. Minus 45.1 hours. So then what's that going to be? 12 minus 5 is 7. Borrow the one from the 3, 2. Then 12 minus 4 is an 8. Right? Did I do that right? 87.4. That's like just in my mind type of calculation. And then 1 hour is 3,600 seconds. So that means that star and planet are wobbling every 87 hours. What is that? That's about 3 days. Every 3.5 days, they're going around each other, right? 87 hours, that's about 3 days, I think, 3 to 4 days. So then convert hours to seconds. 1 hour is 3,600 seconds. So 87.4. 87.4 times 3600. Okay, so it's 314,640 seconds. 314,640. 314,640. So let's write that in the whiteboard. 314 on 314 seconds, 640. Okay, is that the number they had on the simulation? Yeah, it's there. 314. They wrote it in scientific notation, 3.146 times 10 to the 5th. Okay. Now the mass of the star was given. So now let me show you how to do this whole calculation. So then you're going to take the P and you're going to divide it by that number that they gave you, 4.19 times 10 to the minus 9 times 10 to the minus 10, right? So, and then the mass of the star times the power 2/3, and then time the average K value. So, so that's, so the mass of the planet times the sine of the I is going to be what? So you do the, let me write the equation down. The 80 times the 2.088. Let me take a picture of that. So 80 times 2.088, that's the mass of the star, times 10 to the 30th to the power 2/3 times, that's 314,640 divided by 4.19. You guys are going to become expert calculators from this class. Expert to the power 1/3. Wow, pretty complex formula. So now we take the answer that we got. Okay, so then I could just take the answer that I got on my calculator, divide this by, the order that you do it doesn't matter. I could start with the last portion of the equation, divide that by parentheses, 4.19 times 10 to the power -10, close parentheses. You see that? So take a look at that. That's how you put that all in. And then that's equal to. Then you raise that to the power 1/3. 1 divided by 3. Okay, so yeah, I'm raising that to the power 1/3. Okay, then I'm multiplying that by what? Parentheses, the mass of the star, times 10 to the power 30 to the power 2/3. You see? So then I'm working my way from the right side of the equation to the left side. So 2.088 times 10 to the 30 to the 2/3, right? And then times 80. Oh, there it is, 1.19 times 10 to the 27 kilogram. So that's the mass of the planet. That's the minimum mass of the planet. Minimum mass. That's actually around the same as the mass of the Jupiter. Mass of Jupiter. Because the mass of Jupiter is around 10 to the 27th kilograms. In that order. Okay, so let's see here. You see now, MP sine I is equal to that. Remember, so we don't know the inclination angle, the tilt. In other words, this is true. The MP is equal to mass of the planet times sine of the angle is equal to 1.19 times 10 to the 27. Okay, so now, if the star is here, imagine the star is here, and the planet is the imagine. So let me put it this way. Hold on. Let me erase this. So if the planet is, if the Earth is here and the star is here, and the extrasolar planet is here, and the orbit of the planet around this star looks like this, you see, that means that angle, the plane of orbit is facing towards the Earth, you see. That means if we draw a vector coming out of that plane of orbit, and this, the line of sight from the Earth to the planet, that angle is going to be 90. So then I can say MP sine of 90 is equal to that number. And then what's sine of 90? That's 1, right? That means the mass of the planet will exactly equal that number. But if we find out that the orbit later, let's say we do some analysis and we find out that the planet is like this, let's say it's really tilted. It's like that. This is the plane of orbit. And let's say this is I. This is the vector. And now let's say this is 60 degrees. Right? Then what's going to happen? You're going to have MP sine of 60 is equal to 1.19 times 10 to the 27. And then what's going to be sine of 60? That's, I believe that is rad 3 over 2, right? So it's sine of 60. Yeah, it's 0.866. 0.866. Well, then what does that mean? That means the mass of the planet would be, you divide this by 0.866. That means it's heavier than this. So in other words, if a star that is not necessarily even, if a star is not necessarily even orbiting in a plane that's facing us, if it's causing a wobble with a measured radial velocity of average of 80, right? Average of 80, that means that planet must be heavier in order to cause that wobble, even though its orbit is not facing us. So the more tilted the orbit is, the heavier the planet must be in order to be causing that wobble, you see? So that's why that there's that uncertainty by the sign of the angle of the orbit, of the plane of the orbit. Okay, so now we go back to the desktop. Okay, so now, okay, so this is actually the chart that they're giving you is the chart of the first extrasolar planet ever discovered. Remember, 51 Pegasi was discovered in the constellation of Pegasus. And that was the first extrasolar planet. So they're telling you the mass, one mass of Jupiter is 1.9 times 10 to the 27 kilogram. They're telling you that the mass of the host star was measured to be 2.11 times 10 to the 30 kilogram. That's the mass of the star. Okay. So let me minimize this. Okay, so then we need to, oh, there's nothing to, it's just the chart essentially. Oh, okay. Oh, I like that. You can move it around. Okay, that's really nice. So you could do the same things that they did. What do we need to find out? The peak. So you could take a picture of that, right? The highest peak that will give you the velocity. So that would be one picture. And the horizontal would tell you the hours. You know what? On this one, let's do, it's, we could use the period this way, the bottom peaks. Here and then here, you see? So you probably need here, you probably need 3 snapshots. Right here, there's one somewhere here of the lowest peak right there. I would do like right there, yeah. Snapshot here. Then I would do another snapshot there. Then one over there. And then from there, you should be able to calculate the period of the orbit and the average K value. And then put in all the numbers and then calculate the mass of that planet, which is going around the star 51 Pegasi. So using the Doppler Wobble plot for 51 Pegasi above, what is the period P from the graph? So there's going to be 3 plots, 3 snapshots there. And then based on that, answer these, show your work for the conversion to seconds, and then again, take a picture of your result. Then go to question 2. Using the Doppler Wobble, what is the semi-amplitude of the radial velocity? Again, you have 2 snapshots for that, right? And then show your work for how you're getting the average from there. That's not that much work to show. It's just one of them, K1 plus K2 over 2, you know, and then again, show your result. Question 3, what is the mass of the planet times the sine of the angle in units of kilograms? Then show your work just like I showed for the one that I had, kilogram, then show your result. Then question 4, what is the mass of the planet MP sine I in units of Jupiter masses? Then take the mass that you got and then divide by Jupiter masses. For example, in my case, if I wanted to calculate the mass of that one, the example that they gave over here, well, what is the mass of Jupiter? 1.9 times 10 to the 27. So how would I find that? 1.9 times 10 to the 27. So the result that I got, what did I get? 1.19 times 10 to the 27. So then I could just do, I could take then the ratio So I would say the ratio of the MP sine I, the I letter stands for inclination angle. That's where they're getting I, the word inclination. So MP sine I divided by mass of Jupiter. So in that example, the MP sine I was 1.19 times 10 to the 27th. Then you divide that by the mass of Jupiter, which one was it? 1.90. 1.90 times 10 to the 27th. So that means this is like one of those hot Jupiters. So that's 1.19 divided by 1.90. 1.19 divided by 1.90. 0.62. So 0.62 MJ, Michael Jordan. So you would say mass of Kobe is 0.62 mass of Jordan, right? So Kobe is 62% as good as Jordan. I don't know, but you know those debates. So MJ, mass of, for extrasolar planets, for the heavy planets, Jupiter is the one to compare everything to, right? For light planets, the Earth is the one you compare them to. Okay, so now, so show your calculation for that one too. So you show your calculation for that, and then you just take a snapshot of your result. So always, whenever you have calculations, you always show calculations, how you're getting them. Kepler's third law. So once we have the mass of the planet, we can use Kepler's third law to find the distance from the planet to its star. See, now we're developing this. Once we have the mass of the planet, now we can find out some way to calculate the distance to its star. So we say, once we calculate the mass of the planet, we can use Kepler's third law to find the average distance between the planet and its parent star. Kepler's third law works for any planet around any star. It relates the period P, the average distance between the planet and the star A, which is the semi-major axis of the orbit, and the mass of the star, and the mass of the planet. G is the gravitational constant. If we know A, which is the distance between the planet and the star, hold on, what is A? A, which is the semi-major, okay, yeah. If we know A, MP, and M, we can find the square of the period. Alternative, we know the M, MP, and P. So let's actually just look at the equation here. So P squared is 4 pi squared A cubed over GM plus MP. So this is Kepler's third law. Big M is the mass of the star, and MP is the mass of the planet. And thereby, if you know the period, you can calculate the A cubed, the distance cubed, yeah. So A in this example, so it says here, finding A. In this example, we are going to take the mass of the star, mass of the planet, and the orbital period of the two, and use those values to find the semi-major axis of the orbit A, the average distance between them. We know the following values. So the mass of the star is 2.09 times 10 to the 30. The mass of the planet is 1.18, and the period of the orbit. Actually, they're just basically applying this to the planet we just did, right? In the previous example. So then you put everything in, and then you get that star. Let's see here. 4 pi squared, and then you should be able to take the cube root of that number. Woof! Wow. So let's show you how I would do that for this past example. So let's go back to the let's go back to the beginning from the equation. Let me use this equation. A cubed is P squared G M plus MP over 4 pi squared. Okay, so then, no. Okay, so let me erase some stuff here. Okay, so now I'm going to say, one of the things that also I'm trying to teach you is how to put these in the calculator without getting too scared of making a mistake, you know. So developing confidence in that. So you got here, what's the equation? A cubed is equal to P squared G P squared G M plus MP. So P squared G M plus MP over 4 pi squared, right? So then the P squared, remember the P was the number 304,000 something. I erased it now. I don't remember what it was. I erased it. But it was essentially, well, the book had it in the scientific notation way. but mine was a little bit better. I think it was around 304. The book says it's about 304,000, the example. Yeah, 304, 2, 3, yeah, 304,000. But I would prefer using mine, but I erased it now. So 304,000, let's just say 000, then you got to square that. So keep that in seconds. G is the universal constant of gravity, which we've used before, 6.67 times 10 to the minus 11. Okay, the mass of the star was this, and that one, remember, they just gave that 2.88 plus times 10 to the 30 plus the mass of the planet around the star was that one, 1.19 times 10 to the 27. Then divided by 4 pi squared. Okay, so then we can now erase this. So then we're going to have here a cubed. So let's put everything into the calculator. Okay, 304,000 squared times 6.67 times 10 to the power negative 11 times parentheses. Now, when you have to sum things up, then you need the parentheses, right? Or you need to raise something to some power. Well, here actually I didn't put the parentheses. Yeah, you don't need the parentheses here to raise it to the power 2. So yeah, the summing is very important to put parentheses. So then you put here 2.088 times 10 to the power 30 plus 1.19 times 10 to the 27. Close the parentheses, right? Nice. That looks nice. Then divide that by parentheses 4 times pi squared. So you need to put both of these on the parentheses to make sure that they're both in the denominator. You see, you got to make sure they're in the denominator. Then close the parentheses. There you go. So that means this is equal to a cubed. So when you're showing me the work, first write down what you got for the a cubed, 3.262 times 10 to the 29. 3.262 times 10 to the 29. Then you lift this to the power of 1/3. Oops, sorry, not 1/2, 1/3. And then you raise this to the power of 1/3. And then A is equal to whatever that number to the power of 1/3. So then you go, so now you go to the power, parentheses 1 divided by 3. Now, the reason I put parentheses there is because if I don't, you'll think I'm raising it to the power of just 1, you know. I believe I should put the parentheses, yeah. So 1 divided by 3. So basically, that's like saying take the cube root of it. Okay, now what's this in scientific notation? I don't want to write all those numbers. That's 3 spaces to the left. 3, 6, and then 3 more, 9. That's 6.88 times 10 to the ninth power. 3, 6, 9. 6.88 times 10 to the 8th. 6.88 times 10 to the 8th power, and that will give you in meters. So that means that planet is very close to its star. It's to its host star. Remember, the distance from the Earth to the Sun is 1 AU. Earth to the Sun. And what's that distance, 1 AU? It's 1.5 times 10 to the 11th meters. Wow. So if you compare this to ours, that's almost about not 1,000th of AU, but it's a lot smaller. It's almost 100th, but a little bit more, less than 100. A little bit smaller than even 100th AU. So that planet is very close to its star, very close. It's probably just burning up as we speak. So is that the answer they got? 6.88 times 10 to the 8. Should be, hopefully. Go forward. Yeah, there you go. 6.89 times 10 to the 9th meters. Okay, start. Oh, so we're focusing on 51 Pegasi here. 51 Pegasi. So then, using your answer for the mass of the planet in the early exercise in kilograms and the period in seconds, along with Kepler's third law, find A cubed. So just like I showed now, show the work for that, and then your answer and what your result was. And then question 2, now find A, the semi-major axis. So then cube root that, get the answer. Again, show the work for that, and then what you got for the answer. Convert the answer for the semi-major axis in units of kilometers. So then change it to kilometers, it's saying. That's pretty easy. Just move the decimal over, right? And then question 4, remember that 1 AU. Convert the semi-major axis to 2 units of AUs. Remember that 1 AU is that many kilometers. So how would I do that for my particular example? So then it would be, then once you get the answer in meters and this meters, well, you could also divide them in meters. Don't even convert them to kilometer. But since they're asking to convert to kilometer, we could do A is 6.88 times 10 to the 5th kilometers. So you subtract the number of zeros by 3, and then the AU is going to be 1.496, right, to be more exact, times 10 to the 5th, no, times 10 to the 8th kilometers. So if I want to convert my distance to AUs, I use the conversion 1.496 times 10 to the 8th kilometer is 1 AU. And the kilometer cancels the kilometer. So then I divide 6.88 So 6.88 times 10 to the power 5th divided by 1.496. Oops. 1.496 times 10 to the power 8. Right? Close the parentheses. So you're just taking a ratio to convert it. Wow, so you would say it's 0.0046 ratio, 0.0046 of an AU. Oops. So that'd be A would be 0.0046 AU. That'd be very close to its star. Okay, so then show that work, how you convert it to AU, and then put in the answer here and your result. Okay, let's see. Is that, I think that's it for this section, huh? Oh, okay, so then we exit out. Planetary transits. Did we do that? Oh, no, no. Now we're at the planetary transits. So if the planet crosses between the star and the Earth, called the transit, it will block out some of the star's light, allowing us to know that we're seeing the planet's orbital plane nearly edge on, right? So in those cases, in those few cases where the planet's orbit is in such a way that it's facing towards the Earth, the planet will actually transit between us and the star, and it will block out the star's sunlight, right? So a planet transit occurs when the planet crosses between us and it's the star, so that it blocks out some of the star's light. Oh, it's so fast. You see, it's coming between us and the sun. Of course, Mercury is so small, it's not really blocking out the sun's light that much, you know. So it doesn't do anything to it. Hey, but another object transits the sun and it really blocks out the sunlight, right? And that's a solar eclipse. Solar eclipse is actually when the moon is transiting our sun. It's blocking out the sunlight. Now that one we actually notice, you see. But Mercury transiting the sun, we don't notice that much. So light curves. Planetary transits can also give us an idea of how big a planet is. That makes sense because the bigger the planet, the more it will block out the star's sunlight, right? So it will block out its host star's sunlight. A planetary transit seen from Earth in an extrasolar system is rare, you see. But such an event allows us to learn much more about the system than we could determine from Doppler measurements. The first observation of an extrasolar planetary transit occurred in 1999. So notice, remember I said 1995 was the Pegasi, the Pegasi 51? That wasn't discovered by the transit method. It was discovered by the Doppler shift. So a Jupiter-sized planet was found passing in front of the star HD 209458. It absorbed part of that star's light, making the star appear less bright. Astronomers took several precise measurements of the star's magnitude versus time using a telescope and photometer. The decrease of light output caused by the transit, the dip in the center, is small, corresponding to only about a 1.5 to 2% of the full light output from the star. Oh, okay, so you're seeing here the event happening. You see a dip in the brightness. Just love this stuff. Love, love, love it. If we can observe a planetary transit, then we would know the inclination angle, I, of the planet's orbit is about 90 degrees. So you see, a transit happens mostly only when that angle is 90. So this angle means that MP sine I, which we found using Doppler Wobble method, is about MP. The mass of the planet, since sine of 90 is 1. In addition, if we know how fast the planet moves around its orbit and the time the planet takes to move the length of its own diameter, then we can determine the planet's diameter. Oh my gosh. So now we not only have the distance from the planet to the star, we not only have the mass of the planet, we actually have the size of the planet, you see. On the transit life curve, the time the planet takes to move its own diameter can be determined by looking at the amount of time the light takes to drop to the dimmer level. This drop starts just as the planet begins to move in front of the star, and then ends when the planet has moved the length of its own diameter to be completely in front of the star. So maybe let's zoom in on this a tad bit. So, okay, the planet is which one now? The planet is the red one. It's going around its star. You see, right here, you see here, the brightness hasn't even dipped yet. See here? Then it's gonna dip. You see here? So every time this red planet is coming in front of the blue star, the red planet is transiting it, you see? Behind it, in front of it. You see here? Now you see how the dip begins? The dip begins. Oh, I like that we can take step at a time here, you see? Now, this is really nice that we could go step at a time. Oh, there you go. See, this is how you study it. You just go step at a time to see what's happening. As the planet, you see, as the planet is coming in front of the star, watch. See, the dip is starting. See, it's starting. The brightness is dipping all the way down. You see, it's going down, down, down. Okay, when the planet is right centered with the star, the dip has reached its minimum. You see? Then go, then go, then go, then go, and the transit is almost done. Then now the planet goes around, around, around. It comes behind the star. It comes behind the star. And now the star transits the planet. In other words, the star comes between us and the planet. Now another dip begins. But it's not that big of a dip. Ah, you see that? You see that dip that it took? Because the star is the brighter object, the star dipping the planet, the star coming in front of the planet, doesn't dip the system's brightness as much. Now the planet comes in the front. Now the planet comes in the front. Big dip is about to start again. There you go. It's over. Okay, now you go behind. Now the star coming in front of the planet, right there. Dip is about to begin, but very small dip. You see there? It's how it's going down. Barely noticeable. Then another dip. Then it comes back out. There you go. Oh my God. And this is actually a star, a real star called Algol, the binary star system Algol. Actually, these are two stars. They're dipping each other. They're eclipsing each other. Algol is actually a binary star system. So it's not just a planet orbiting the star, but it's two stars orbiting each other. Man, just amazing. Algol. Okay, so now let's see here. So this is the figure shows the time versus relative flux brightness plot for a transit of a star by an extrasolar planet. Click on the plot to get the time and the relative flux at a point. Okay. So let's see here. Okay. This is showing you here. You see the brightness? Okay. Maybe I should minimize it, huh? Oh, there it is. Okay. So the relative brightness, you see, it's right now it's 1. So what does a relative brightness of 1 mean? Nothing is eclipsing anything, you see. So nothing is eclipsing anything. So then the planet is coming in front of the star. So the dip starting, then it comes out, and then the planet is fully out. But I don't know why it gets the data gets very uncertain here. These are error bars that you're seeing. Error bars, that means the brightness we can't really tell as bright as that or as dim as that. Those are called error bars in our data, or maybe instrumentation. There's something. These error bars are smaller here. So the brightness, this is the regular brightness dipping and then coming back out. Okay, then some questions based on that. Use the transit of HD above. Determine how long it takes for the light to fall from full light to minimum light during the transit. So basically from here to from full light right here. So you have to read this. How many days is that? The middle is 0 days. So we're talking about 0.05 days, right? 0.05 days is when the drop starts. Or maybe it starts, well, no, it looks like it starts here. Or maybe it starts there, the drop. I think the drop starts right here. So maybe that's what, negative 0.05, negative 0.0, I'm going to say negative 0.055 days. And then let's say go all the way down to the minimum brightness. So somewhere, well, this is when it gets back. This is when it's back to normal right here. You see? So I think this is the normal one right here. And then this is the other normal one. It's already fully out. So I think this is kind of midway right there. Although this is dimmer, that's true. But that might be an error thing too. There's an error bar. I think this should be the middle right there. And then it goes back out all the way to here. You see? So it looks like it's 0.055 days, something like that. Then you convert that to each day is 24 hours. You multiply it, and then you multiply it again by 3,600. Each day is 24 hours. Each hour is 3,600 seconds. Okay, so then you put the number here. But here for this one, they want to go from full light to the minimum. So that means show a picture of this, photo of this right here, and then a photo of the middle right there. And let's say this is the minimum right there. I would go like this. I would go probably up like that. So that's the minimum right there. Something like that. That would be the minimum. So then based on those two pictures, you can answer that and then show your answer and what result you got there. From the Doppler observations in earlier section, it was known that the semi-major axis or radius of this planet orbit is this. What is the circumference of the orbit? for this problem, treat the orbit as a circle. So they already gave us the A. I guess they did this problem before. So then once you know the radius of the orbit, how do you calculate the circumference? 2 pi r, right? 2 times pi times this distance. So show your work for that and show your result for this. Let's show you result for the answer for this. From the Doppler measurement of the orbital period is known to be 3 times 10 to the 5 seconds. What is the average speed of the planet as it orbits the star? So then the average speed, you take the circumference and then you divide it by the time. So the whatever answer you got here, then you divide it by that time. So show your work for that and show the average speed and your result. So then question 4, what is the diameter of the planet in meters? Planet diameter. Oh, okay, so then how many seconds did it take for the planet to start here and go? See, the planet started its orbit, the dip started right here, right? So if I want to know the diameter of the planet, what do I have to do? So if the planet starts here, right? And then this is the star. As soon as the front edge of the planet gets in front of that star, the dip begins, right? The dip in brightness starts like this. So then by the time that you are like the dimmest is when that planet is like centered with the star. You see? It's like that. And it's covering the right in the middle, you see? So the planet is like that. Then when it goes back up, the planet is like that. So basically, if I know the time that it took to go from here all the way to here, right? All the way from here, all the way to here, then we're gonna say distance traveled is equal to velocity times time, right? So what's the distance traveled by this planet from when the transit first occurred to when the planet is completely out? What's that distance? So the planet has to travel what distance? Well, it has to travel across the star, right? Then it has to travel another distance equal to its diameter, you see? So the planet's distance that it's traveling is equal to the diameter of the star plus the diameter of the planet. And that's equal to its velocity times time. Front end. Yeah. Let's see here. Do we know the diameter of the star? Planet diameter. Let's see, did they give us the planet's diameter? We know how fast the planet moves around the planet and the time that the planet takes to move the length of its own diameter, then we can know the diameter on the transit light curve, the time that the planet takes to move its own diameter, and the amount of time the light takes to drop to the dimmer level. starts just as the planet begins to move in front of the star and ends when the planet has moved the length of its completely in front of the star. In front of the star. Yeah, it says this drop starts with just as the planet begins to move in front of the star and ends when the planet has moved the full length of its own diameter to be completely in front of the star. Oh, okay. I see what they mean. So basically what's going to happen is there's a couple things going on here. Hold on. It's okay. Here's what's happening. So let me show you guys. So as the planet okay. This is very clever stuff. So when the planet first starts its so let's see here. So when the planet is like this, and then the star is like that. Okay, as the planet starts to come in, the brightness is like this, then it starts to dip. You see? So as the planet is going like this, like this, like this, like this, like this, and then the planet is fully in. Yeah, the planet is fully in. Then that means it's gotten as dim as it's ever gonna get. So it's like this, it says dimmer. I'm kind of doing this because the error bars show that things are not exact numbers, Then it's dimming. When the planet is fully in, it's the most dim that it's ever gonna get. When the planet gets here, it's not gonna get any more dimmer. Just because it's on this side of the star, this doesn't mean that this part of the star is any brighter than that. So that means as the planet is traveling this way, all the way until the front edge of the planet reaches here, then it goes like this, the brightness like that. So it stays plateaued, you see. Then when the front edge of the planet reaches the star, then it starts to get dimmer as the planet is coming out, you see. Then the brightness starts going back up like that. And then when the planet is fully out like this, then it's basically fully out and goes like that. So in this case, we don't have to calculate the diameter of the star. We can if we want to eventually, but we're focusing on calculating the diameter of the planet right now, of the planet. So here's what we can do. We just take the time it took from here all the way to the dip. Forget the plateau. You see, forget the plateau. So from here to the dip is what matters. And then from here to here is also going to be the same amount of time. You see, coming out or going in. We're not going to worry about this time because that's the length of time to traverse the star. You see, there you go. So now going back, was I right when I go back in question 1 when I said, how long does it take for the light to fall from full light to minimum light? I was wrong. Not thinking too hard. I was wrong. Yeah, you see there? You got to go like this. Go back. Okay, so now go all the way to when the dip is starting. You know what? The dip is probably starting right here. Yeah, like coincides with the planet. When the planet gets to the edge of the disk, there you go. The dip starts right there. So that's how many days. So take a snapshot of that. That's negative 0.5, negative 0.6. What you can do when you take a picture, draw little lines because they don't have the small little lines. So take a ruler or something, draw little lines. That way you can guess how many days that is. That looks like negative 5.5, negative 0.6, maybe negative 0.65, negative 0.67. It's almost negative 0.7, you see. So you want to know how many, write down each of those small lines. So that's when the dip starts. And I want to measure all the way when the dip has ended. Maybe right here, actually. Then after that, the plateau, it's plateauing. Well, the dip has ended around here. And then after that, I believe it's plateauing like that till about here. And then it starts on the rise again, all the way to there. This is the rise, you see. So like that all the way to here. So this is the plateau region. You see, from here to here, I would say. So I think the dip ends, I'm just gonna guess here. I think the dip ends around here, I'm feeling like. It's not that easy to guess because again, the error bars make it hard. I think the dip ends somewhere like that. Then you can take a picture of that, draw the little lines, take the difference, and then take those days, convert them into seconds, you see? There you go. So then I was wrong over there for the first question. Then you go to question 2. Basically, you calculate the circumference. Then over here, you calculate the average speed. Question 4, find the diameter of the planet. So then how do you translate that to the diameter of the planet? Well, you just say, since we've already calculated the average speed, distance is equal to average speed times time. So then you say the diameter of the planet is whatever average speed I got times how many seconds it took from here to here, to go from here to here, which that's the one that you got. And then you multiply them. So show work for that and you get the diameter. Okay, then you go to the question 5. What is the radius of the planet in Jupiter radii? Then you show work for this. Divide your radius by the radius of Jupiter so you can show how you're getting the ratio. Question 6, what is the volume V of the planet? So then again, show work for this in cubic meter, how you're getting the volume of the planet. And then question 7, now from the Doppler measurements, the mass of the planet is known to be 1.33 times 10 to the 27 kilogram. What is the planet's density? So you see, once we know that the planet transits its star, everything else follows from that. We can calculate so many things. Okay, so a lot of calculations on that one. But the only 2 pictures, I believe, just 2 pictures, 2 good pictures with the lines showing, that would be nice. Okay, so then, and then actually the pictures for each of the questions, the results for each of the questions, and the work, a lot of them had work to show, you know. Okay, now I think one more. Problem with hot Jupiters. The vast majority of the planets we find are Jupiter-sized planets orbiting extremely close to their stars, so-called hot Jupiters. Unfortunately, because of the limitations of our observational technique, we cannot be sure if such problems are common or if these are the only planets that we can reliably easily find. The planets discovered so far around normal stars tend to have Jupiter-like masses and lie rather close to their parent star. This finding suggests a situation different from our solar system, in which the massive Jupiter-like planets are at a larger distance from the sun, right? I mentioned that earlier. This anomaly has been called the hot Jupiter problem, since in these extrasolar systems, we see giant planets that are near their parent star and therefore strongly heated. So the most extrasolar, I think this is the last page. Oh, that's good. We're near the end. This was a kind of a longer lab so far. Most extrasolar planets discovered so far are gas giants in close orbits around their parent stars. The Doppler experimental methods in use are sensitive only to more massive planets and are most sensitive to large planets. We refer to this fact as an observational bias. Presumably, there are also smaller planets orbiting other stars, but our present observations are biased towards seeing the more massive ones. Data from the Kepler mission has been released since the beginning of 2011. Much of it is still under analysis. However, over 3,000 planetary candidates have been identified, and it is expected as time goes on, this number will only increase. Hopefully, we will soon know whether the hot Jupiter problem is merely one of observational bias. In other words, are we just happening to discover planets that are closer because they're easier to discover? Or do a lot of them actually just exist that don't have small planets near their stars? Maybe we're the exception, where the small planets are close to their stars. Who knows, right? We could be the exception in the universe, you know? So observational bias exercise. Oh, just one question. Which of the following scenarios would also be a good example of an observational bias? Select all that apply. Well, I guess it's just one question. So select all that apply and then show your result. What you think is your result. So that's pretty much it. Nothing to show in terms of work, just your result for this one. Cool, quick ending. Nice stuff, man. Nice stuff. Wow, extrasolar planets. It's amazing how much we can discover just by some analysis, right, from Earth. Okay, guys, thank you.